So our final speaker for this session is Nathan Killoran. Nathan is the head of software and algorithms at Xanadu, and he's one of the founding developers of PennyLane, the world's leading quantum machine learning software library. Nathan steers Xanadu's open source quantum software products and leads algorithm research in photonics and quantum machine learning, and also runs QHack, an annual quantum machine learning hackathon. Nathan holds a PhD in physics from the University of Waterloo with expertise in quantum computing, deep learning, and quantum optics. And today he's going to be telling us about software for quantum machine learning. With that, I will turn it over to you, Nathan.
Great, thanks, Paul. Everyone who's in the chat, welcome. If you can't see my slides, just call out to me in the chat and I'll see that. But otherwise, let's get started. We only have about 25 minutes and there's lots of exciting stuff to chat about. So today we're going to talk about software for quantum machine learning. Okay, so just a slight digression before we start about Xanadu. This is the company that I work for and the company that's hosting this quantum stream at TMLS. We are a quantum computing software and hardware company, and we have our own quantum photonic chips that we provide over the cloud. We are proud citizens of Toronto, based in Toronto, and backed largely by Canadian venture capital funds. So if anyone's interested in hearing or seeing more about our company or learning about working with us, check out the links at the bottom there. In terms of what we do, we're building two things. We're building quantum hardware and quantum software. So on the quantum hardware side, we have photonic quantum computers, and these come in both in near-term variants that are imperfect and noisy, but very interesting. And also we're building towards a blueprint of fault-tolerant quantum computers, like what Alba described in her talk earlier today. And on the software side, our major effort is PennyLane. And PennyLane is a quantum machine learning software library in Python that allows you to connect your favorite machine learning library like TensorFlow or PyTorch to various quantum computers from different providers and to run quantum machine learning algorithms. So in terms of the topic of software for quantum machine learning, I really want to go back to motivation that I have entering this field from deep learning. So actually, I noticed in Alejandro's talk earlier, he had a very similar slide where he was talking about what made machine learning successful and deep learning successful. And I'm missing one of the points he had, which was data, but the other three are here, which is hardware advancements, workhorse algorithms like backprop, hardware obviously is things like GPUs, and then specialized software that allowed people to really rapidly prototype. So from my perspective, those are the three main things that really helped boost and make machine learning successful and deep learning in particular. So in deep learning, you have the workflow where you have a neural network. It's a function, it's a model, a mathematical model with free parameters. You define a cost function, which somehow connects your model's performance to some training targets. And then your algorithm to train your model is gradient descent. So gradient descent is the standard technique for training neural networks, and you have to compute the direction of steepest descent in the parameter landscape. And then after you have done gradient descent, which follows the gradient step by step, you hopefully have arrived at a local minima, which can be used, or a global minima, if you've done well, which can be used for classification or prediction at inference time. But I want to think bigger than that. I want to say deep learning is great, but actually it's a small piece of a larger perspective. And the larger perspective is that any code should be trainable, not just machine learning models. We should be able to optimize any scientific program. And this is the idea of differentiable programming. So in terms of differentiable programming, how does it differ, or how is it similar to deep learning? Well, the main difference is actually that instead of having a model, which is a neural network, you have a classical function, a scientific piece of code that does some mathematical function. And this doesn't have to be a model. It could be something like a graphics engine, for instance, that does something very mathematically heavy. But you can still train it using the exact same techniques. So that's the idea of differential programming, training not just a mathematical model, but training code itself. So there already is lots of software for differential programming on the classical computing side. You're, I'm sure, very familiar with TensorFlow, PyTorch. There's lots of different libraries available. The key feature, I would say, of pretty much every one of these libraries, the thing that makes it most powerful is this notion of automatic differentiation, which means that the gradients that you need to compute of your model or of your code in order to optimize, those things are automatically handled by software. You don't have to worry about them. So how can we use the same ideas to make quantum machine learning software? So in quantum machine learning, we have similar things that deep learning had going for it. We have hardware advancements. We have new quantum processors that are becoming available in the last few years. We can actually steal a lot of the same algorithms that are available from deep learning, like gradient descent, and apply those to quantum computers just as easily. And there's also an emerging software space for quantum machine learning. My company Xanadu makes Penny Lane, but there's also TensorFlow Quantum. There is Alba spoke this morning, her group at U of T. It's making a software library called Tequila. There's a number of software frameworks for quantum machine learning emerging. So how does it actually work? What do these quantum software frameworks do? The key idea is you start with a quantum circuit. A quantum circuit consists of a sequence of gates, and these gates are parameterized. So you have some free parameters, and those form the free variables of your model. And then you measure some final output of the circuit. And I don't need to get into too much of the details here, but the relation of the final output to the parameters is a linear relation. The outputs of a quantum circuit are depending linearly on the parameters of the gates. Or to say it differently, they depend continuously on the gate parameters, which means that they're ripe for the same optimization tools that we use in deep learning. So a quantum circuit, you can picture a quantum circuit as some kind of black box that very complex internal mechanisms, but essentially it's something where you feed in data to your gates, the free parameters of your gates, and you get out some final value of some function that happens to be classically intractable. And because these are differentiable, the ideas of differentiable programming apply, which means that we can train quantum computers the same way we train neural networks. We can use the same tools. The kind of key technical step you need in order to train a quantum circuit is you need to compute the gradient. And the function that a circuit implements is classically intractable. So how can we actually compute the gradient? And it just turns out that there's this trick. It's called the parameter shift rule. It says that the gradient of the circuit can be determined via querying the circuit at a slightly forward shifted value and a slightly backwards shifted value for a particular parameter. This is not the finite difference method. This is a macroscopic shift that we're doing here, but it's the same kind of intuition. You can shift forward, shift backwards, and subtract, and that actually gives you the gradient. And this is a simple rule that can actually be done automatically by software. So that's the pieces we need actually to train a quantum circuit. We have a circuit, and we want to compute its gradient, the gradient of the function that that circuit implements, and we can do that using this parameter shift rule, which means that we just subtract two circuits that have the exact same architecture but shifted parameters. And the value of that difference gives you the gradient. And then we can train the circuit using gradient descent. Once we have the gradient, we can use the standard tools of classical gradient descent to optimize the circuit and move it towards a particular point in parameter space. This is actually called a variational circuit, this routine that I just described. And it's the kind of the first class of algorithms that you learn about in quantum machine learning on today's devices, of these variational circuits. And they're often considered as hybrid models, hybrid quantum and classical models. And the reason for this is because you are putting in classical data, you are running something on a quantum computer, and then you're measuring out classical data, and your optimization proceeds via some classical computation, which is gradient descent. But I said this is only the first tier of hybrid algorithms. You can actually start thinking of more complex variants of this simple variational circuit by allowing the classical model itself to be trainable as well. Right? And this actually gets us into the notion of arbitrary hybrid quantum classical computations. You take a trainable quantum circuit, you combine it with a trainable classical model, and you can build an end-to-end trainable hybrid model that incorporates both classical and quantum computation in it. So how does it actually work under the hood? If you've ever dug into something like TensorFlow and you've used a tool called TensorBoard, you might have seen pictures like this one on the slide here. This is called a computational graph, and this basically maps out all the steps in your machine learning model. So you might have a linear layer, you might have a convolutional layer, a pooling layer, and so forth. And that's what all those steps are being mapped there. And you can think of it as a graph where each function that gets applied to the data is a node in the graph, and the flow of data between those two functions, the input-output relations, are the edges in the graph. And this is called the computational graph. So this is the kind of idea we can start using to build quantum machine learning software, is we start replacing some of those nodes in that graph with quantum computers or quantum circuits. We call this a quantum node, right? It's basically where a larger model hands off something to a quantum computer. The quantum computer executes, you evaluate some function on that quantum computer, and then it returns some output, and that gets handed back off to the classical machine learning library, which maybe does some further classical processing. And the other ingredient you need is, if you want to train this quantum circuit or this hybrid model, you need to be computing the gradient as well. And as I said, the gradient can be computed using this parameter shift rule. So this is the magic. There's nothing too deep here, but this is what happens to make software for quantum machine learning. Is you start with a tensor object, for instance, from Torch or from TensorFlow or maybe a NumPy array. You pull out just the numerical value. So you throw away all of the class structure that those machine learning libraries have, and you just pull out the data. You feed that data to a quantum computer, and you run that circuit enough times to return a certain value, an average value at the output. That average value is then taken back, rewrapped into this tensor object, and sent further down that computational graph in, for instance, TensorFlow or PyTorch. So that's how it works, is that, just like you might have data that is sent to a GPU for computation, you can also take data and send it to a quantum computer for computation, and then it gets returned back to the overall model. So this is actually all of the pieces we need to make fully end-to-end differentiable hybrid models in classical machine learning tools that connect to quantum computers. And it can all be done automatically. So in classical machine learning, we have this backpropagation algorithm. And what backpropagation does is it starts at the last step of your computation and it goes backwards. It follows the arrows, the blue arrows in this diagram, the ones that go backwards in the flow of the computation. And at every step, it has to compute the derivative of the outputs of that step with respect to its inputs. And then it combines these together using the chain rule from calculus. And so if one of those steps happens to be a quantum computation, that's okay, because we know how to compute the derivatives, or we know how to compute the gradients of quantum circuits. So we can stitch those things together seamlessly. So now it's maybe illustrative to go through a hands-on example of how this works in practice. So in order to actually show you, I'm going to have to pick a software library. So this is the one I'm most familiar with. This is the one we built at Xanadu. It's called Penny Lane. And it's an open source Python library that allows you to connect classical and quantum resources together to make hybrid models and to make quantum machine learning models. So I encourage you to check out our website if you're interested, or also check out our GitHub. The basic example I want to walk through is very, very simple. So it's got a single quantum bit, a single qubit. And what we do with this quantum bit is we apply 2 rotations. So a quantum bit can be represented on this block sphere as an arrow on the surface of the sphere. And what we're going to do is we're going to rotate around the x-axis by some variable, and we're going to rotate around the y-axis by some variable. And those 2 variables are going to be free parameters. We're not going to know what they are. We're going to train them such that the qubit flips from pointing at the North Pole to pointing at the South Pole. So how does that look in code? Well, the first thing we do, it's Python, so we have to do some imports. So we import Penny Lane. In this particular example, we're going to use Torch as the machine learning library of choice. And we need to tell the software which quantum device we want to use. So a quantum device can be either a quantum computer. In this case, in this example, this is a Forest QPU provided by Rigetti. But it can also be a simulator. So a classical code that is simulating what a quantum computer would provide. In either case, you can use either one. So that's the first thing, is do our imports and create the device that we actually want to run these computations. And this is similar to telling TensorFlow that you're using CUDA to connect to some GPU that you have. The next step is actually creating the quantum computation. So as I said, the quantum computation is a circuit. It takes some inputs. In this case, we have the 2 rotation angles, phi1 and phi2 in this example. And I said we're just doing rotation. So we do a rotation about the x-axis on that sphere and rotation about the y-axis on that sphere. And we use the name wires to refer to the different qubits in the circuit diagram. And then we want to return the final result of the quantum computation. In this particular case, is the expectation value or the average value of some measurement of a particular observable quantity. So that's the definition of our circuit. It's a very functional interface like you might be used to in PyTorch or TensorFlow. And then we have to tell Python that actually this thing should be run on a quantum computer. So that's where we use this QNode decorator. So we're able to say that we want to run on the device that we defined above, and we want to use a torch interface. And then the rest is actually just classical optimization. So if you've ever used torch before, we're just defining a cost function here. We're defining two variables as torch tensors, saying that they're trainable by saying that requires grad, and then we were use the atom optimizer to train it for 300 steps. So this is boilerplate stuff. This is stuff you'll find in every machine learning tutorial, and it doesn't really matter that you're training a quantum computer here. So what this ends up doing is you see that we're able to push this qubit state represented by this arrow to the top or the bottom of this block sphere. And to make it a bit more interesting, we keep switching the target partway through the training time, so it has to keep adjusting. But you can see it's very easy for it to find where it needs to go. So we're learning the right angles to rotate it down to the spot where we need to be. And in the bottom right corner here is actually a picture of the optimization landscape and different runs through that landscape. So you can actually connect these ideas uphold for pretty much any machine learning library, as long as it's got enough feature set to allow you to register custom devices and custom gradients. So NumPy is obviously a standard one in scientific computing. You can use NumPy for this kind of quantum machine learning training. And of course, you can use PyTorch and TensorFlow. So in terms of different looking circuits or different looking programs, when you're working with different interfaces, this is an example of the same program coded in PyTorch using a Forest QPU device, and then the program being written in NumPy and using a simulator called default qubit. And you can see that really, other than swapping the devices that we're using and maybe a little bit of difference in the boilerplate between the optimizers and the way you would code that in PyTorch versus the way you would code it in NumPy, you're really doing the same thing. So it's really not too different to code it up in the two different frameworks to run the same optimization. So that's an overview of how quantum machine learning software as it exists today works. If you are interested in learning more about quantum machine learning, we actually spend a lot of our time thinking about how to build the community in quantum machine learning. How do we train more people? And one of the reasons we're speaking here at the TMLS is that a lot of the ideas that we're using in quantum machine learning, they rely almost more on knowledge of machine learning than they do on knowledge of quantum computing. So I personally, in my history, I started as a quantum computing student. I started in my PhD studying quantum computing. And eventually I went on to do a postdoc at U of T in deep learning. And so I was able to make the connections, the things I was seeing in deep learning and the things I had learned in quantum computing. And I think it's much easier for people with a machine learning background to learn quantum computing than the other way around. I think that it's not non-trivial. So learning quantum computing is it does take some effort, but it's just linear algebra. And quantum machine learning is mostly just optimization applied to those linear algebraic settings. So I really feel that the background you get from coming from machine learning works very well for learning quantum computing. And the other way around, it's a bit harder. I think people with a quantum computing background don't necessarily have the basis to learn machine learning. It's a little bit more foreign to them. So we're definitely trying to think of ways we can build up the quantum machine learning community. And that's why we want to reach out to the machine learning practitioners and data scientists and everyone from the classical computing side, which maybe wasn't exposed to quantum computing, but is now getting interested in that. So to that end, we actually spend a lot of our effort creating educational materials for learning how to do quantum machine learning. So we start with the very basics, things like, what is quantum machine learning? And even answering that question is not trivial because as a practitioner, there's actually a whole spectrum of things that qualify as quantum machine learning. And depending on your interests, you could land at different points along that spectrum. So you could talk about, how do I use tools from deep learning like I just described now to train today's quantum computing devices. So that's one flavor of quantum machine learning. You could also start thinking about, if I had a fault-tolerant quantum computer with 1 million qubits, then I could run very powerful linear algebraic algorithms, which would give me a speed up in classical machine learning problems. I could train, or I could run certain matrix manipulations much more efficiently using a quantum computer. So that's a bit further in the future, but it still qualifies as quantum machine learning. So there's quite a broad spectrum. We tend to focus on what you can do today. What are the ideas around today where you can start coding and getting your hands dirty and actually working with today's quantum devices? So we also, in addition to covering all those key concepts that you need to learn, and I've just discussed a few of them now in this talk, we also have tons and tons of hands-on demos. So part of our mandate, our mission on our team is actually to educate, but we also create some of these new ideas. We look at what ideas we can take from deep learning and port them over to work for quantum computers. And it's actually been a very profitable way to study things. So if you're looking at some of these are some tutorials from our website. If you're looking at some of the names, you probably recognize them if you've got a machine learning background. So quantum transfer learning, can we use the ideas of transfer learning in the quantum setting? There's something here called doubly stochastic gradient descent. And that one is, again, using ideas from classical machine learning, that stochastic gradient descent can be used as a way to train quantum circuits. And in deep learning, you would just have something called stochastic gradient descent, and doubly stochastic here just refers to the fact that there's two things that are stochastic. You're stochastically sampling a mini batch of data, but you're also stochastically estimating probabilistic quantities, average quantities, using a small subset of samples and not a full exact quantity. You can also make classifiers out of quantum computers. So if you had a machine learning task where you wanted to classify a data set, you can make those in quantum computers. So there's lots of things. Actually, another one I should mention is quantum GANs. It's another idea that emerged out of our team. So we really want to put all the ideas out there so people are empowered to learn more about quantum machine learning. And the hope is that by doing that, we're actually going to build up the whole field together, and all of the discovery that has to happen, all of the research that needs to be undertaken can be done faster if there's a bigger community working on it and they have tools at hand. So this goes back to the original slide where I said, what are the things that we need for quantum machine learning? And I said that we need hardware advancements, which we have. We have quantum devices becoming available. I said we need algorithms. And I think that largely we can port over most of the algorithms from deep learning to the quantum case. And then finally, we have the software, and that software is the final tool, final piece of the puzzle that allows the community to actually start contributing back. So that's why we build the software, is actually to empower the community to help us along the journey. Just as a final note, we also organize events related to quantum machine learning, and we just announced our second iteration of our QHack Quantum Machine Learning Hackathon taking place in February next year. So if you're interested in that, please check out the website. We'll be announcing some more details shortly. We've got lots of exciting speakers lined up for that. And it was really a great event last year, and this year we're going virtual, so it should be open up to a much wider audience as well. Great, that's it for me. I think wait for Paul to maybe beam back into the building here, but I'm happy to take everyone's questions.
I'm back. Thank you, Nathan. That was awesome. A lot of questions coming through in the chat. So
oh, great.
The first one, which I think is probably a common one, is, are there any issues doing quantum machine learning with quantum hardware when, quantum hardwares could lose their state after a short period of time? Like, how do you maintain state in the quantum computer to do quantum machine learning, or is this a problem?
Yeah, for sure. This is something you have to keep in mind. The deeper a quantum computation gets, the deeper the circuit is, or the more qubits you have, the more susceptible you are to noise. So obviously we want to improve our hardware progressively over the coming years, but that's still a presence there. So it's something you have to worry about, not even in quantum machine learning, but quantum computing in general, is this decoherence that can really degrade your algorithm, the noise that can degrade your algorithm. The bright spot is that actually with quantum machine learning, the quantum machine learning tools don't necessarily assume a particular model. They can actually adapt to what they're seeing. So they can potentially route or find their way around noise in the system. They can find their way to different values of the optimization parameters that are more noise tolerance. So there's definitely a lot of hope that by using the machine learning tools, we can no longer have to hand design algorithms and hope that they work with error, but actually work with the error hand in hand.
Okay. And another one about integrating something like Penny Lane into a more traditional classical machine learning environment. Is there a speed up that you would get from doing that? How would that help, say, someone doing traditional machine learning?
I would say right now it's still very much an exploratory phase. So the tools that we provide right now, they allow you, which is really cool actually, they allow you to connect to quantum computers from your machine learning libraries. In terms of what you would do with that, that's actually the question. That's why we built the software. Is we want to solve those questions. We want the community to crowdsource those ideas. But to me, that's already exciting enough. That the fact that we can do this, and this wasn't even available, say 2 years ago. 2 years ago was when we first released Penny Lane. So just over 2 years ago, you didn't even have the ability to do this, and now we do. Right. So this is hopefully empowering us to a discovery phase where we can actually start to find and explore more rapidly those use cases where we can find some potential advantage. But I would say, really, you're waiting for the hardware. So if the hardware is not of sufficient quality, it'll be hard to find advantage. But as soon as the hardware is of quality, of a level of quality that's beneficial, then you're unlocking all that power.
So you touched on this in the talk, but maybe you could say a little bit more. So like, with learning about quantum computing, you need to study things like superposition, Grover's algorithm, but do you need these things for quantum machine learning? How critical is it to know about these topics, and how much can you get away with?
I'd say you can definitely get away with a lot more in quantum machine learning, because you can, as long as you're choosing a circuit that is known to be very rich in its expressive power, that can create lots of entanglement, to create lots of superposition, then it can actually become more of a heuristic art. You can actually just try to bash your head against different data sets and see how well it learns. The more you know, obviously the better you can do. Just like in classical machine learning, if I know that I'm processing image data, natural images, then a ConvNet is much better to use than a vanilla neural network. And that's because you're taking advantage of the structure. So obviously, the more structure you know about the problem set or the data set or the problem you're trying to tackle, potentially the easier you could find your task of training a circuit. But you don't necessarily need to know Grover's algorithm or Shor's algorithm or anything like that.
Sounds good. Good news for me. Maybe I can handle this one. When will Xanadu release a consumer-grade quantum computing platform, or will it purely be provided as a SaaS model in the cloud in the foreseeable future? In terms of exact timelines, that's hard to say exactly when, but absolutely our roadmap is to provide a consumer-grade quantum computing platform. If you've visited our website, I'm sure we have images up there. You can see our hardware. It fits into a standard consumer rack. There are still some steps to go through to move away from some of the cooling components associated with our detectors, but our hardware is based on light, and so we don't need cooling for the chip itself. The cooling is for the detection. There is a roadmap to move away from that. So eventually we can stick this into a standard electronics rack, and you can have it sitting right next to you. Exactly when? Let's say the next 0 to 20 years, plus or minus some number.
I think your answer there, Paul, is as soon as someone shows up and they are interested in actually purchasing the on-site, the on-prem hardware versus having the cloud deployable model, they're willing to pay that price tag, then it's something we can definitely do. It's the technology is there for that.
That's the real answer. Yeah, it's ready. If we'll talk offline, Mark. We'll hook you up. This is a good question from Ricardo. I actually had this one as well. So in which ways is Penny Lane different from TensorFlow Quantum or Tequila? You talked about a number of different frameworks. So what differentiates, pun completely intended, these different frameworks?
Yeah, maybe before I say what differentiates them, maybe I should say what's similar. So TensorFlow Quantum, Penny Lane, Tequila, they're all working on the same principles that I outlined in my talk. They're using these automatic differentiation tools. And beyond that, it's largely a matter of feature set And just like, some people prefer TensorFlow or PyTorch for classical machine learning, there might be various reasons that you prefer one or the other. I can say that at least for TensorFlow Quantum, they are, obviously it's a Google product or a Google service or software that they provide. So they are connecting their quantum computing library, Cirq, with their machine learning library, TensorFlow. And if you don't like either of those two, then that's kind of not going to be your jam. So PennyLane does have the feature that you can connect whatever machine learning library you like and whatever quantum computing hardware you like together.
Yeah, I really like that picture that you often show as the puzzle pieces with PennyLane at the center, really joining all these pieces together. Is a good way to think about it. Another great question from Danielle. Can you speak briefly about the residency program and how much can an undergraduate student expect to learn during the program?
Awesome. I love the question, actually. The residency program is our internship program for next summer. So it runs from May to August, and likely it'll be a mix of on-site and virtual, depending on obviously external society circumstances. But we're planning to have a cohort of residents who are going to be working with our team on internship projects for the summer. It kicks off with the Quantum Machine Learning Bootcamp. So if you just got a flavor today, we'll have a more dedicated session during the residency program. And as an undergraduate student or graduate student or even an experienced person from industry, you would expect to learn a lot during the program. The team is world-class, and working with them as your mentors would exponentially boost your skill set for sure. So lots of exciting stuff to learn if you join the program. And you can check out the testimonials from former interns on our residency website.
Thank you for that, Nathan. Yeah, the deadline for applications is December 15th, I believe.
Yep.
Yeah. Awesome. Okay, if you are new to QML, how do we select either MSFT, Q#, IBM Qiskit, Xanadu, PennyLane? I mean, the obvious answer is you pick PennyLane, but maybe Nathan can give a more diplomatic answer.
Yeah, it obviously depends on what you want to do. So there's now a number of hardware providers that are available, and they work on different physical implementations. So ion traps, superconductors, photonics. Depending on which kind of systems you want to play with, you might choose one or the other. In terms of software, I would say try them all, actually. Like, try the ones and see which ones fit your style, your workflow, your needs. We definitely focus heavily on fantastic documentation, so we hope that you would find our documentation helpful and continue to use PennyLane because of the wealth of resources available there. But I definitely encourage you to try them all. They're all really pushing lots of new ideas in the space.
Excellent. We've gone over time a little bit, but I think that's well worth it. I think that's it question-wise. Oh, we've got one more question about the type of qubits we use. So I'm guessing you mean at Xanadu. Yeah, so Alex, we don't actually use qubits, we use Q modes. So we use the modes of light for doing quantum computation. And so technically we don't use, they're not really qubits, they're qudits because they are multi-level systems. That's a whole nother hour talk on Q modes and qudits.
It's okay, Paul, we got time.
We got time? Oh, what's that? Oh, okay, well, apparently I've got to go. Anyway, thank you so much, Nathan, for participating. Thanks to all of our speakers, also Alba and Alejandro. Again, if you have any more questions for us, you can hit us up on the Quantum Slack channel, TMLS, the booth as well. And you can even, you can DM me or Sefer Tagavi, and I'd be happy to talk at any point this week. And thank you again, TMLS, for hosting this first quantum computing and quantum machine learning session. Hope we have more in the future. Thanks, everybody, for sticking around. Have a great conference.
Thanks, everyone.